In this set of videos, we're going to practice the free response questions from the 2013 AB Calc exam. So if you haven't done so already, pause the video and read the question a couple of times through. There are no shortcuts. If you don't read carefully, you will for sure make mistakes. So what I've noticed in this problem is that we are given a rate function. So this is the rate at which gravel is coming into the plant in tons per hour. So I'm thinking of it already as a first derivative. And there's a second rate given in the problem. That's the rate at which gravel is being processed and leaving the plant. So that is always 100 tons per hour. And then there's a very important hidden value here that at time equals 0, there's already 500 tons of unprocessed gravel at the plant. And we're working over an 8-hour day. So I've got a rate in, a rate out, and an initial value. All right, so then if you would stop and think about putting this into your calculator, because as I look through the parts of the problem, I'm going to be asked to find the derivative of g, so that's actually going to be a second derivative, tons per hour, and then we're looking for a total amount that arrives. So I see the net change theorem. Remember, if you accumulate a rate, you will get a net change. And in part C, the amount of unprocessed gravel, is it increasing or decreasing? So I'm going to have to check the value if a derivative is positive or negative. And in part D, a maximum amount of unprocessed gravel. So we're going to have to use, find out when the derivative, find the critical numbers, and then check using our closed interval test, value of the derivative at the endpoints and at the critical number. So I know I'm going to use g and I'm going to use g prime. So whether you get a lot of things into your calculator at once or whether you do them one at a time, that's certainly your choice. But we definitely know that we're going to want g of t in our calculator. So that's going to be my y1 function. As I'm typing it into the calculator, think of your window. So cosines are between -1 and +1, but here the amplitude is multiplied, so it's 45. And then this 90 shifts the whole value up 90 units. So I know there's a maximum y-coordinate of 135. I have also determined that I'm going to do the derivative of y1, so that's going to involve a sine value. So I know that sines are going to be negative, some values are going to be decreasing when cosine is increasing. So as I set the window, I would cover the 8-hour day. So I like to see the axis, so I started at -0.5, but that would certainly be your choice. And I want to see up through 8 hours, so I want a little larger than 8. And then for my y min, only because I knew I was going to do a sine function as the derivative, I went below the axis. But you can always come back and adjust these later. But remember, we knew our maximum value was because of the amplitude plus the 90-degree shift, so to cover the 135. So I picked 150 as my y max. So the closer you can get to a window the first time, just saves you some adjustment. So there's our y1 function, which represents g of t. That's the rate at which gravel is arriving at the plant. So I'm going to work on question A here to find g prime of 5. And I'm going to use g prime later in the problem also. Sorry, I keep losing my calculator there. So I'm going to go to, I'd like to see what that function is. So I'm going to go to the home screen to find the derivative. So remember that you're going to use your derivative symbol. And then don't forget that you have to have the argument with respect to x. So then once I have my derivative function and my TI-89, I'm going to use green diamond copy. And then I'm going to go to y2 and paste it in, green diamond paste. And then the derivative will be there for all parts of the problem. But there's many different ways you could use your calculator. All right, so now I'm going to remember that y2 is g prime. So you can check your graph if you wish to see it there. You could now find g prime of 5 from your graph screen. So if I wanted to find, I could trace the second function at 5, but I think most of us would probably go to the home screen. And now I want to find out what y2 at 5 is equal to. And I'm going to do green diamond, enter always to save some time here. So that would be our answer for part A. I'm going to pause while I write that. Let's clarify here that when we do g prime, it's the derivative of a rate. G itself was in tons per hour, so its derivative is in tons per hour per hour. So when you interpret what it is, make sure if you say the word decreasing, then take out the negative sign. So the rate at which gravel is arriving is decreasing by 24.588 tons per hour per hour. So we have to be very precise on the units there, or of course that answer would not be marked correct. All right, in part B it says find the total amount of unprocessed gravel that arrives during the hours of operation on this workday. Well, we know the workday goes from 0 through 8 hours, and the rate at which gravel is coming in is simply G. So this sounds to me like the net change theorem. If you accumulate a rate, you get the net change. But here it says total amount, so you might say, do we need absolute value? Do we accumulate the absolute value of the integral? And there's two ways to answer that question here. You can put the absolute value into your calculation. Let's go back to our graph though, and notice that G of t was always positive, so the absolute value signs really don't make much difference, but I think you would want to explain that in your answer. So either put in absolute value into your integral, or say since g of t is greater than 0 over 0 to t less than 8, the total amount arriving is the integral from 0 to 8 of g of t, and I guess I should use capital G as it was given. And we're going to calculate that. So go to your calculator again, and home screen probably, and then find your integral. So we're going to integrate, and here we're using y1 of x with respect to x from 0 through 8. And I'm going to do green diamond, enter. And then we're going to transfer that. That's going to be the number of tons that have arrived during the day. So I'm just going to pause while I write that answer. In part C, we're asked for is the amount of unprocessed gravel increasing or decreasing? So the amount of unprocessed gravel, we're going to have to come up with a combination of the in and the out. So the question here really is, are we processing it faster than it's coming in or more slowly than it's coming in? So let's think about this. The rate that it's, let me pause. The rate that gravel is arriving is our g of t function, and the rate that it's leaving is the 100, and these are both in tons per hour. So we could come up with another function that would be the difference between the two of them. So we could, whatever you want to call it, we could say that we want to compare these two values. We could create a third function, or we could simply say, well, what is g of 5? And I can grab that from my calculator. So from my home screen, I can find out what y1 of 5 is pretty simply. And green diamond, enter. So that is approximately 98.1407 tons per hour. And that is less than 100 tons per hour. So I guess that answers the question. So I guess we just explain it. So the amount of unprocessed gravel is decreasing at t equals 5 hours. Okay, so if there's more going out than there is coming in, does that make sense, I hope? I think that answers the question well enough. All right, and then we've got to go to part D. What is the maximum amount of unprocessed gravel at the plant during this workday? So this is finally where we have to remember that there were those 500 tons of gravel sitting at the plant before the day even began. So now we've got to come up with an overall combination of things here, and then we have to find the rate and the critical numbers. This is our closed interval test. So let's think of how we're going to put this all together. This, of course, is the challenge part of this problem. So what could we say here? Could we say that the amount of unprocessed gravel at any time t, we start with our initial 500, and then we're going to add the difference between what's coming in and what's going out. So I've already used t here for our variable of this accumulator function, so let's put x here. This is our rate of gravel coming into the plant. That's the rate of the gravel coming out of the plant. So just like we did in part C, can't we take the difference between them? That would be the unprocessed leftover. And sorry, that should be a dx right there. All right. So what we want to do then is find out when this is at its maximum value. So that means at a critical number. So to find critical numbers, the critical numbers, we need to find out a prime of t. Well, that I can really do faster without my calculator. So the derivative of 500 is 0, and the derivative of this integral, this is our fundamental theorem. So we can see that that's going to be right back to g of t minus 100. So we want to set this equal to 0 to find our critical numbers. A prime of t is equal to 0 when g prime of t equals 100, right? So how do you want to find that on your calculator? Well, you could use the solver on your calculator, or you could use the trace on the graph. I'm going to show you one additional way here. If I turn on my calculator and go to the Y editor, if I want to know when something is equal to 100, I could, oops, sorry, I'm not where I want to be here. Let's clear that. I don't want to be in the home screen at all. I want to go to the Y editor, and at 3, oh, I am in the Y editor, sorry. And at Y3, I want to just put in a horizontal line of 100. Sorry, that was a little confusing. So we'll see what it looks like here on the graph. Maybe that'll make it more clear. So if I want to know when is g of t equal to 100, can I do that just by finding this, the x-coordinate of this intersection right here? So that's one common way. Not the only way, of course. There's probably 10 different ways you could have found this out using just the the home screen and the solver for 1. All right, so if I want to find the intersection of graph y1, yes, hit enter. Not y2, so I'm going to use the up arrow. I want to get to 3. There we go. And 3. And then I need a lower bound and an upper bound. And that will be our critical number. So again, I'm going to jot that down. I'll pause while I transfer that to my paper. So what was I doing there? I was finding the critical number. A prime is equal to 0 at this point. So we also have our closed endpoints then. So now we've got 3 candidates we want to test. Remember what we were trying to find is when is there the greatest amount of unprocessed. So at time 0, I already know that one. Before the day started, there were 500 tons of gravel. And now our critical number is in the middle. 2, 3, 4. I guess that would have been enough digits. And then our other closed endpoint is at 8 hours. And now I'm going to use my calculator to find these 2 values. So I'm actually going to calculate this function. So you could put that into your calculator as y3, or this could be the integral of y1 if you do that in your home screen. So let me pause and get that in the calculator and then I'll show you. All right, let's look and see how I just did this in the home screen. I just put in my function 500 plus the integral of y1 of x, because that's our g of t function. We've already got that in our calculator. So g of x minus 100 with respect to x from 0 through, and then our critical number is my second limit. So this gives me the amount of unprocessed gravel, 635.376, and then I'm going to come back to my calculator and I'm just going to change that upper limit to an 8 to find this other value. So I'm going to pause and write those both in. So I've written in those 2 values, and it's very important that you realize that you would not get the points for this problem if you didn't show that you tested the endpoints and the critical number. So some sort of diagram, chart, or ordered pairs, but you're comparing 3 different y coordinates in order to come up with the maximum. So here we were looking for the maximum value, not the minimum value. So make sure that you write your conclusion to answer the specific question, and that should do it.